Ultra-high cosmic ray is a very, very high energy cosmic ray. So which the energy, so we can imagine what kind of astronomical object accelerate up to such kind of energy. But one of the most important feature of the ultra-high energy cosmic ray is even in the galactic magnetic field goes rate. So there is a possibility to trace back the source. So that is ultra-high energy cosmic ray for us.
So important is actually in astrophysics to understand the source. Actually, first we should see the source, and then if we have some counterparts in optical or something, then we can understand what kind of object could accelerate particles at so huge energy. So then we can understand the magnetic field, we can understand maybe hadronic processes which are behind, whether it's from black holes or something else, and that's very useful tool if we can find some sources.
Anyway, we need more statistics to confirm the mass composition. And another thing is, so still we don't know the hadronic interaction model at their energy. So maybe after the LHC, we could confirm around the 10 to 70 electron volt. But after that, we do calculate the hadronic interaction model by the extrapolation. So so we need confirm the hadronic interaction model. After that, we extend the our experiment to get the large acceptance or something.
And I think also the next step is in trying to do that event by event, because now it's just averages over all the events because the statistic is too low. So if we can increase the statistic and also improve the detector, like measuring the muons for all events, then you can probably get the mass at least between heavy and light, even by event, and then you can in an easier way do correlation to find a source, because then if you do correlation only with the light one, it should correlate, and if you have some heavy mixture, then it's difficult to have any correlation. So if you can extract the light component of the mixed composition, that is seen in OG for the moment, then you could really get to an astronomy with charged particles and try to find the source, which is one of the goals of the high energy cosmic ray.
It is a difficult question for me. So at least I can say our result is consistent with the pure proton QGS-2 model, QGS-2 or 3. That's all we can say. So, but we need to understand why there is a difference between the OJ and telescope array. So we have a different concept to analyze the mass composition. So their OJ's method is sophisticated because they use fiducian volume cut. But here we couldn't do that. But at least we estimate the acceptance bias by the detailed Monte Carlo. So I don't know, this is the reason why our result is different, but we should contact each other and to understand what do we do. So yeah, this is and I hope we want to conclude this kind of discrepancy in the near future.
Okay.
So, and I'm sure that it will be solved with this working group we have together between the telescope array and Pierog Observatory. We already know that a bit more than that. We know that that telescope array is compatible with proton QGZ2-3, but we know that it's also compatible with Auger mixed composition with the current statistic. So with higher statistic, we will know really whether it goes in one or the other direction. And thanks to LHE, as we said, the model improved, and now the QGZ2-3 is not really the best model that we know. So, and using, for instance, the next version of QGZ2, if we just keep the same model, then the interpretation of the result will be much more similar. Because we need to keep in mind that the data themselves are really close to each other. So it's just a question of what type of model you put there and of error bar size. So I'm sure that, yeah, in 1 or 2 years this will be solved.